interval, and I'll discuss it with you what the interval is, divided by 1.64. These are the numbers that were computed, that are based on all those mathematics or all those equations, all those empirical formula that we haven't discussed though, but they are there. So interval divided by 1.64. But as my confidence level increases, see here, as my confidence level increases, the chances of standard error decreases. So if I am 90% sure, then the standard is the interval divided by 1.64. If I am 95% confident about my claim, then the standard error should be lower. Then it is equal to interval divided by 1.94. If I am 99% sure about my claim, then this denominator is still higher, is higher than these two. So the more confident you are about your data set, the more confident you are about your experiment, the more confident you are about your claim, your data set should be higher, you have higher number of data points, and you should have lower standard error. What this interval is? This interval it varies from I should say from experiment to experiment, from your from the field to field. Sometimes it depends that if it's a very, and also it's like, if it's, let's say we are designing a nuclear facility, right? We want to collect some sample size of the radiations, of certain radiations. Now radiation, wherever the human safety is concerned, we have to be very confident about our claims, because we cannot take chances on human lives. So if it's about nuclear safety, or it's about anything which is very much concerned about the human safety, then our interval size, our interval is actually the chance of error that we think we can tolerate, or this standard error here. It's also called the tolerance level. How much? This interval here is also called tolerance level. How much error can we tolerate? If it's plus minus 1 that we can tolerate, or we can tolerate plus minus 5, or we can tolerate, like in height, well, if interval is plus minus 5, it's not going to harm anyone. However, if it's a nuclear facility, or let's say if it's something related with the speeds of the vehicles, then this higher speed of, if we are not very much sure about if we are not 90% like we are sure about that data, then that could be dangerous to the human lives as well. So this interval varies between among the problems that we are defining, among the areas that we are doing our experiments on. So let's say that our tolerance level, it could be plus minus 1 mile per hour for the speed, or our tolerance level is plus minus 0.5 about the radiation. I don't want to be wrong more than 0.5. So my tolerance level is 0.5. So that is the interval. That is the tolerance level. That is what I can tolerate. So I have to be very, very sure. Okay, I have to be, this is the margin of safety. This is the margin of safety. The higher risk is involved in any phenomena, the lower the tolerance is, right? So let's say if we are 95% sure that our estimate of the speed mean has 1 mile per hour error, let's say that is what our claim is, that we say that whatever data we have collected, whatever sample size we have collected, whatever data we have collected, the speed, the mean speed, when I compute the mean of all those speeds, then it has plus minus 1 mile per hour error of being different from the population mean, right? Because remember, let's go now, going back to our lecture 1, that we assume that our population is a representative of, our sample is a representative of our population. So the tolerance here in this case is 1 mile per hour. I can tolerate 1 mile per hour error, plus or minus. So if I'm saying that the mean speed is 7 miles per hour of my sample, then my population mean is either 8 miles per hour or it's 6 miles per hour. Okay, so the tolerance that I have here is 1 mile per hour. So standard deviation of the speed sample is, let's say, 7 miles per hour. Then the standard error is 1 divided by 1. Okay, this is not even important here, but let's say standard error is equal to 1, which is the tolerance, divided by 1.96. Now, why this 1.96? Because I said I am 95% sure. These are the derived equations. These are there. 1.64, 1.94, 2.58. I cannot make change here. So if I am 95% sure about my claim, then the standard error is 1 divided by 1.96, which is equal to 0.51. Now the standard deviation of the sample of the speed that I have collected, I know I computed it, is 7 miles per hour. Then the required sample size is 7 divided by 0.51 squared using this equation. The required sample size is 188. Now if I have collected 200 data points, I am good, I am fine. I can say yes, my claim, I am 95% confident about my claims now. But if I have collected 150 data points, then I need to collect 33 data points more. Okay? So is it clear now? How do we compute the sample size? So we compute, so here are the 3 things. Go out and or do an experiment, or from any source, collect some data points. Let's say 10, 11, 12, whatever you can in a given period of time. From that, then you define the tolerance level for your experiment. One is the confidence level that you say where you are 95% sure, 90% sure, 98% sure. Then you say the tolerance level in my case, or in this case, it could be defined by different case studies that you do. That tolerance levels in this phenomena, or for this phenomena, is 1, or is 2, or it's 0.5, or it's 0.1. You compute the standard deviation of the sample that you have collected, and then you find out the standard error, depending upon whether you are 90% sure, whether you are 95% sure, whether you are 99% sure. You compute the standard deviation, and then you find out the required sample size. Standard deviation of the sample that you have collected divided by the standard error, and that gives you the sample size. Now, if the data points that you have collected are less than the required sample size, then, which means it's an indication that for your claim to be 95% sure, or your claim to be 98%, or your claim that you are 90% confident, then you go out and collect more data points. If you have collected more data points, then what is indicated by this number here, then you are good to go with your experiment. Then you can make claims based on your confidence level, whatever confidence level you have selected here. Is it clear? Okay, good. Everybody? Okay, thank you so much. So, this is what our lecture was about today. I don't think that SPSS gives you it has the tool to compute the sample size. However, it can give you this. It gives you the standard error. It gives you the standard deviation. Using those values, you can compute the sample size, and that is how I computed the sample size. Like when I did my dissertation, I found out that in the beginning, I used all these, and the tolerance level was, again, it is defined for my study. It was defined elsewhere in the standards that we have for for transportation planning. Now let me give this example to you. For transportation planning, something which is at the planning level, something which is not there, we are thinking about the future. Our tolerance level increases. We say, okay, fine. If the speeds are plus minus 3 miles per hour, we are good. However, when it comes to the operation point, when there's something which really exists in the field, and then we are studying it, then our tolerance level reduces, because now we are really talking about the safety. Though in the planning, of course, we are talking about the safety, but it's at the planning level. There are many factors involved there. However, when we are talking about something which exists, then it's over there the safety is the concern, time is the concern. Of course, there are many things. When I'm putting money into something, then I have to be sure about it. Then my tolerance level reduces. So again, tolerance level depends upon the type of the problem that you have defined. For example, you want to clean the let's say our experiment. It depends. It's based on our experiment is defined as finding out the BOD level in river Ravi. Now, BOD level, or the level of the like different bacteria or biomass, is of course important, because it's something, or let's say any pollutant in the air or any pollutant in the river. It's very important for human health. So our tolerance level in that case reduces. And so if the tolerance level reduces, which means that our standard error should also be low. Our standard error should also be low. If we want our standard error to be low, then our sample size should be higher, right? So for my experiment, for my claim of being 90% sure or 95% sure or 98% sure about my experiment, then I need to find out the required sample size. Okay, so if I do so let's do a recap today. What we did, what we studied. We studied the different the different measures of central tendency, which is mean, mode, and median. Then we studied the measure of dispersion. Now, what is the measure of dispersion? It shows the dispersion in my data. It shows the spread in the data. It shows the deviation in the data. So we computed the standard. We learned how to compute the variance, and we learned how to compute the standard deviation. Standard deviation is based on variance. However, we do not use variance because it's a squared term. We do not usually define anything in terms of the squared. It's not common. So we find out the standard deviation. Then we learned what is the normal distribution, why it is important, because most of the natural phenomena are defined based on the normal distributions, until and unless we have any error in our data collection process or any error in our experiment. So to know whether our data set or our sample, is it normally distributed or not, we find out, we draw it, and then we look at the shapes, whether it's skewed positive or towards, whether is it symmetrical. If it's not symmetrical, which way it's skewed, and what is the kurtosis. Because knowing these parameters are important about being more confident about your data. Knowing your data is very important before even analyzing it. So now you know your data. You say, okay, my data is not very much deviated from the normal, so maybe I do not need to transform the variables to develop the model. However, if your data is highly deviated from the normal, then you may have to use the non-parametric, the models which are exclusive for the non-parametric data sets. Or you may have to transform your variables so that you can apply the parametric models develop, or you analyze your data set as we analyze the parametric data sets, which somehow follow the normal curves. And so skewness, kurtosis, the way you draw the normal curve, that everything tells you what your data looks like, or what is the distribution of your data set. Then we learned about the standard error. Though the concept was pretty difficult, but I hope that you all understood it. So, and why do we want to know the standard error? The reason we want to know the standard error in our data set, because we want to be okay. Yes. Okay, yes, I have given you the control. You didn't get it? Okay. Let me see if I can.